Yeah, thanks so much, Jen. Thanks for the invitation to give this talk. Really excited to share some of the work that I've been doing with all of you as a member of the NEID and HPF instrument teams, mostly in collaboration with Chad Bender, Joe Ninen, and Leo Paredes on accurately modeling the telluric absorption in the spectra across the visible and near infrared, in particular accounting for the variable and quite complicated line spread function of the instruments. So I guess just to start off with kind of, get us all on the same foundation, in case anyone isn't aware, kind of what do I mean when I say telluric absorption? What is telluric absorption, telluric contamination, right? Ideal world, we have a star that we're interested in learning about. It has some intrinsic spectrum that we want to get information from. So we point our telescope at it and boom, we learn what we want to know. But of course, it's not that easy because there's a lot in between the star and us. There's a lot in space between the star and us, but in particular, close by, Earth's atmosphere is in the way. And Earth's atmosphere will absorb some of the incoming starlight before it reaches our telescope. And this is exactly what I mean when I say telluric contamination or telluric absorption. It's molecules in Earth's atmosphere, such as water, a kind of example transmission spectrum of is shown here in a region for water. But those molecules will absorb some of the starlight at particular wavelengths, depending on the constituents of the atmosphere along our line of sight. And so once we get the spectrum into our instrument, it's actually contaminated. It is no longer just the intrinsic stellar spectrum, but features from Earth's atmosphere are overlaid. And so that can seriously inhibit the information, the astrophysical information that we can get from our observations. This is quite a widespread problem across the spectral bandpass that we're normally interested in. Here I show kind of the full range of visible through near infrared. Really, these are the NEID and HPF bandpasses, and transmission through Earth's atmosphere for multiple molecules. And you can see the transmission for much of the spectrum, particularly into the near infrared, is quite low. So we are losing a vast majority of the astrophysical information in these stellar spectra in the red part of NEID and into HPF. Here in blue is water absorption. That's definitely the most significant absorber. You can see these extremely saturated bands, but there are, of course, other molecules absorbing as well, some oxygen bands in the visible, and then into the near infrared, you start getting other molecules such as methane here in teal and carbon dioxide in orange. But I think it's also important to note, particularly kind of for our purposes in EPRV, that this is not just a static contamination. It is not just that you are losing a bunch of your spectral grasp, but that this effect is also temporal. And one reason is because of barycentric motion. So the relative location of star lines, here in an example spectrum shown in blue, the relative location of those compared to telluric lines in red will change over the year as Earth moves in its orbit. As Earth is moving away from the star, its lines will appear red shifted, and then as Earth is moving towards it, it will appear blue shifted. And so stellar lines will be contaminated differently at different parts of the year. And then, of course, exactly which telluric lines are contaminating depends on the systemic velocity as well. And so if you either don't mask for your tellurics or you have a poor correction, then those residuals will impart noise with a yearly period, which certainly can cause problems for time series analysis of your data. It's also true that the telluric absorption strengths are often seasonal. Here I show just a plot of the water vapor column at McDonald Observatory at the Hobby Eberly Telescope, where HPF is for a few years. And you can see that there is this pattern where in the summertime, the water vapor is quite high. In winter, it's quite low. There's a lot of variation over the night. Water vapor can vary quite dramatically over just a single night, but there are these broader seasonal signals as well. And this is just for water. You see the same thing for NEID here in Arizona during the monsoon season, but this is also true for other things such as, the vegetation life cycle and carbon dioxide. And so this can be quite a problem. You need to be able to either accurately mask or remove this noise to make sure that you are not imparting some temporally coherent signal that you don't want onto your data. So just to highlight a couple examples of how telluric contamination affects kind of some of the science return we're interested in. Kind of first, just to highlight a single important spectral feature. This is something I come back to a lot. This is the near-infrared helium triplet, which is a very important, increasingly important probe of atmospheric mass loss. Here's an HPF observation of B1298 tau, a pretty important benchmark young planetary system. So very important target for understanding early atmospheric evolution. This line right here is the helium feature broadened by fast rotation and high activity at youth. So great, HPF covers this line. You can get it from the ground. You could observe transits and look for a planet's evaporating atmosphere, right? That's wonderful. But that's not the spectrum we observe. The spectrum we actually observe is in pink. And this right here, directly overlapping the helium feature, is a very strong, relatively strong water line that, depending on the relative motion between the Earth and the star, the telluric line can directly overlap the helium feature, greatly inhibiting your ability to measure a planet's evaporating atmosphere. And so having a telluric corrected spectrum for your atmospheric analysis would be quite important. Now, you can also look at the effects of telluric contamination on maybe something a bit closer to home in terms of activity indicators and time series analysis of them. And so here, this is a GIF courtesy of Jacob Lunn, but this is a portion of the NEID spectrum near H alpha. And the bottom here are zoom-ins on the core of H alpha, and then the two reference regions that we use to measure the activity index for H alpha, right? Basically just the relative depth of the line. In blue is a telluric corrected spectrum, and then in black is a time series of the telluric uncorrected spectra. And you can see that both in the reference regions and across the core of the line, telluric features sweep in and out. And so this will impart the temporally coherent noise I was talking about earlier and hamper the time series analysis you can do with the activity indicator. Here is the time series of the indicator value, and you can see that without the telluric correction, the values are quite noisy. They have some pretty large deviations that somewhat match up kind of phase-wise over the year. And sure enough, if you do a periodogram of this time series, there's quite a strong peak at a year and then aliases of a year. So without a telluric correction, we're gonna have this yearly period aliased into any of the signals that we're trying to pull out in the activity indicators to detrend, issues, stellar jitter in our PRV observations. So that kind of highlights some of the issues with tellurics that can affect the science we're interested in with these high precision, high resolution spectrographs that we use. And so we need to find a way to correct, for this. So how do we do that? So there are a couple different ways that I'll talk about now. One way to correct for telluric contamination is through empirical models or data-driven corrections. This is typically done by, say, observing a host of hot stars, such as A stars, which, because they are hot, rapidly rotating, They don't really have many spectral lines of their own other than broad hydrogen features. Here's an example of an A-star observation with HPF. In red is the Telluric-corrected spectrum, and you can see that it's quite flat, except for this passion line. I believe it's passion. From hydrogen here, and that in black is the observed spectrum. All of these narrow features are telluric absorption. And so you could build up a library of hot star spectra that you could then interpolate over or model with to correct telluric contamination. There are also some codes and methods out there that leverage barycentric motion itself to disentangle the intrinsic stellar spectrum and the telluric absorption. And then you would often, couple these grids perhaps with PCA or linear regression to apply the correction from, say, a library of stars to particular observations. And so there are some pros and cons to this. The pros are that this directly reflects your observations. I mean, you are using observations from your spectrograph to correct other observations from your spectrograph. So any quirks in the instrument are already accounted for. You don't need to know any molecular absorption physics, which, at least to me, after attending the HyTran meeting earlier this year, doesn't sound too bad. I definitely am not up to date on my quantum transitions. But there are some drawbacks too. I mean, exactly that, having no absorption line physics information, it is nice that you don't have to deal with it, but it is also a drawback because especially after talking with atmospheric physicists, molecular physicists, these line lists are perhaps better than some of us believe. And so if we have this information, it would be important to wrap in. And then, of course, you're limited by the signal to noise of, say, your spectral grid that you observed, and observing those hot stars, or in the case of leveraging barycentric motion, you need pretty complete time series covering the full barycentric throw. These methods can be quite observationally expensive. So another way to do it is to use synthetic transmission models of the atmosphere. And so this would be by performing some line-by-line radiative transfer modeling, using line lists of molecules in the wavelength range that you're interested in, and then fitting for parameters of the atmospheric model, whether it be the atmospheric profile, abundances of different molecules, fitting for those parameters and then generating a model. And so here's just an example in part of the NEID bandpass of two models generated through line-by-line radiative transfer through the code LBL-RTM, in blue at low water vapor, red high water vapor. And so you get these quite high fidelity models. So, right, the pros of this, you have your exact telluric spectrum. You can tie every single line to information in the input line list. And so you know what transition, what molecule caused the contamination that you're interested in. And these are quite high fidelity corrections. But there are also some drawbacks here, right? These models are not perfect. They are quite good, and I'll show later on kind of where they succeed and where they might fail. But they are still, the line lists are not perfect. You need to have information about your atmosphere, although I think that's not necessarily a huge issue. And then kind of importantly, you need to have quite intimate knowledge of the instrument you're observing with, right? I mean, these models here, these lines, this is the, kind of natural intrinsic broadening of the molecular absorption line, but once it passes through your spectrograph, it will be broadened by your instrument's line spread function, right? We normally might think of that as just a resolution, but as I'll show later on, it can be much more complicated than that. And so you would need to have a very precise and accurate measurement of your instrument's line spread function to convolve with these models to reflect observations. And that has certainly been a sticking point up until somewhat recently for applying synthetic models for correcting tellurics. So that's kind of a bit of an overview of telluric contamination and how we might correct for it. So the work that I've done has mostly been focused on synthetic transmission model corrections for the two instruments that I work on, NEID and HPF. So just a quick introduction to these two instruments. These are kind of sister instruments, I would say. NEID is in Arizona at Kitt Peak, just, I don't know, an hour and a half that way. It covers the visible, goes into kind of the close by near infrared as well, with on-sky RV precision below a meter per second. And then there's HPF, which is a near infrared spectrograph, covers ZY and J band. It's at a bit lower resolution than NEID, but it's on a 10-meter telescope in Texas at McDonald, the Hobby Everly telescope, with an on-sky RV precision of 1 to 2 meters per second. And so the goal was kind of to have accurate Telluric corrections across the visible and near infrared that can be applied to both of these instruments, and in particular for NEID, applied through our data reduction pipeline to give Telluric models to all of our users that they could then apply to their science. But as I alluded to earlier, generating transmission models is not necessarily the problem here, but having those transmission models accurately reflect your observations is a bit of a sticking point. You need an accurate instrumental line profile to convolve with those models to reflect observations. But there is definitely a bit of a solution now, and by a bit of a solution, I mean a big solution, and that is through using laser combs to be able to fit for a variable line spread function over your spectral bandpass, right? We mostly think of the laser frequency combs as providing a very, very stable, precise wavelength solution, which they do, but they can also be used for some other things as well. And so, right, laser comb lines really are ideal for fitting of an instrumental line spread function. Here I just show an echellogram of the HPF LFC. And kind of what's most important is, right, the laser comb lines are unresolved. And so essentially, the profiles that you observe of the laser comb lines in your spectrum will be reflective of the instrumental line spread function at that point in your spectrum. These laser comb lines, they're uniformly spaced in frequency, so not uniformly spaced in wavelength, but still uniformly spaced across your spectrum. And in the case of HPF, they are spread across the full spectral bandpass. In the case of NEID, it covers most of the bandpass. We actually just recently got an upgrade to our hardware, so our laser comb line light, which used to only go down to about 5,200 angstroms, now goes about 100 nanometers bluer. And so you can go through your spectrum, use this forest of unresolved lines to fit for your instrumental line spread function that you can then apply to your Telluric correction. So just to kind of highlight what I mean when I say the line spread function can be quite complicated, here is stacked LFC lines on the left for NEID, on the right for HPF. All I have done here is across a spectrum. These numbers here are the dispersion pixel over in order. I have chunked up the spectrum and just overplotted laser comb lines in one portion of the spectrum to show how the line spread function is evolving over in order. And you can see, right, like here at the very red end of this NEID order, here at the very blue end of this HPF order, these line profiles are quite clearly non-Gaussian and asymmetric. And so that will certainly cause a problem if you are just kind of evolving some constant resolution Gaussian with your transmission models to try to correct for your Telluric contamination. On top of that, you can see, maybe here on NEID, it starts to maybe get a bit squatter across the order. Its exact shape and width are changing across an order. And so we need to be able to model this over the full spectrum so that you can have an instantaneous instrument profile at any point, and you can then have a full spectrum model reflective of your observations. So how do we define the line spread function model? This is something that multiple people have done. There was a great paper out, I forget if it was earlier this year or late last year, for the espresso line spread function using Gaussian processes. Other teams have tackled this as well. But so for our line spread function, focusing perhaps first on HPF, excuse me, was defined by Joe Ninen, a collaborator, physically motivated based on the spectrograph itself. So for HPF, the spectrograph is fed by a fiber that's terminated with a slit. It then passes through your spectrograph optics and then falls on your detector. And so from this, in an ideal world, you would expect you have a top hat contributing to your line profile from the slit. You have some Gaussian PSF from your optics, and then you have a kind of single pixel top hat response from your detector. But the big question here is the spectrograph optics. As I showed on the last slide, from those LFC lines, it's clearly not a base Gaussian that's contributing to the instrumental broadening. There's something more complicated going on. So to account for this, what we've done is we have a kind of a base line profile that is a trapezoid, reflective of the slit and the pixel response, convolved with a Gaussian, which is your ideal PSF of the spectrograph optics. And then it's multiplied by a basis of orthogonal polynomials. They have been specifically fit to be orthogonal, not to a Gaussian, like a Hermite polynomial, but orthogonal to this trapezoid convolved Gaussian. But these orthogonal polynomials will then account for any optical aberrations across an order and from order to order that introduce asymmetries in your line profile. And so all of this together provides a smoothly varying model of the line spread function across your entire spectral bandpass that you can then fit with the laser cone lines. And so this is quite nice to have this kind of physically motivated model that you can constrain for smoothness, since these things should be varying across your spectrum. So this is the HPF profile. For NEID, we currently are just using a simpler model of a top hat convolved Gaussian. That clearly does not account for the asymmetries present, but it's a pretty good job, especially since the asymmetries in NEID are really concentrated on the edges of our orders. Our detector is quite large, and so our orders go well beyond the free spectral range. But a similar model could be applied and will be applied to NEID data, the only difference being it is directly fed by the fiber. So instead of a slit-like top hat here, you would have a semicircle contributing to your line profile. So how is this model doing? So here is just an example LFC line in the middle, I guess towards the end of an order in HPF. In black is the LFC data. In blue is just a Gaussian fit. And you can see that it's quite bad. It's not accounting for the asymmetries present. And because of that, it's biased a little bit in terms of its centroid. But if we apply this line spread function model with the orthogonal polynomial to account for asymmetry, you see that the fit is quite good. Residuals to the profile fit decrease by about a factor of 10. So this is very, very encouraging. You might think that this model is quite flexible. It is, but because you're fitting all of these laser comb lines across an order together, and if you apply regularization, that kind of smoothing of the parameter fitting across an order really helps to prevent overfitting. Just to kind of highlight that, here are parameters for the NEID line spread function. So again, like I said, this is less complicated, just a Gaussian. Here's the Gaussian full width half max convolved with a top hat, which the box width of the top hat is shown here. For one of the spectral orders across dispersion pixel, you can see what I was saying about here is that the edges of the NEID order or where the profile really starts to blow up beyond the free spectral range, but these parameters are smoothly varying across the order. And so you can incorporate that information into your fitting to make sure that your line profile is not kind of going haywire. So now we have our line profile, just to kind of maybe give a bit of a wrap up on the line profile work. There are still some things that need to be addressed. Like I said, the NEID model is not complicated enough, but we can apply, if not the HPF model, something very similar to the HPF model to NEID. And this will include these new blue orders that were not previously accessible with the laser comb. Something else that I think would be interesting to do is, so these laser combs can be swept, meaning that you can change either the fundamental frequency or the repetition frequency to basically kind of shift your laser comb lines over the spectrum. And so this would be able to more highly sample pixel to pixel variations in the LSF shape over your spectrum. And preliminary investigations don't see anything significant, but I think it will be important to investigate for any temporal evolution in the line profile that you would have to account for, especially perhaps after maybe vacuum cycles or something like that. And of course, the line spread function can be applied not just to Telluric correction, but to many other things as well. Like I showed in that example of fitting the line to an HPF laser comb line, fitting a Gaussian looked quite biased in terms of its centroid. And so that would kind of trickle down into the wavelength solution that you're fitting. And so applying this LSF model to the wavelength solution and calibration should even further improve the wavelength calibration of these systems. This is actually something, there's a paper forthcoming from Winter Parts, a grad student at Penn State, looking into the HPF wavelength solution and how residuals could be tied to line profile effects. You can also, of course, wrap this into spectral synthesis of your stellar spectra, looking for chemical abundances, stellar parameters. I believe this is something that Shubham Kanodia, a postdoc at Carnegie, has been looking into. And you can also apply this to get a more accurate sky emission line subtraction. This talk, I'm pretty much only talking about telluric absorption, but there is telluric emission as well. And this is kind of quite a problem in the near infrared. Even if you have a sky fiber that should be capturing any sky emission in your observation, just subtracting those two things is not often enough. And so you could apply this model to have a more sophisticated sky subtraction and reduce telluric contamination even further. So we now have our line spread function. So that's great. And we can now go ahead and generate and apply transmission models to correct for tellurics in NEID and HPF spectra. So kind of what are the steps of our method? So we have our line profile, that's great, kind of one of the greatest sticking points. And something that, there are codes such as TerraSpec that in the past have fit for tellurics and line profiles simultaneously, but we don't need to do that anymore because our line profile is fixed. And so that removes a lot of free parameters in your models that would make fitting tellurics over a full spectrum quite challenging. So the next thing we need is our transmission model grid that we then can convolve with the variable instrument line profile to produce observation-like models. So how have we constructed this model grid? So what we've done, so we have this multi-dimensional grid, relatively finely sampled in the relevant atmospheric parameters. So these are generated using AER, Atmospheric and Environmental Research, I believe is the name. Their code LBL-RTM, which is the backbone of many of the transmission model-based telluric corrections out there. But it uses LBL-RTM to generate a model covering the full NEID and HPF wavelength ranges. We then downsample that model because it's extremely oversampled in wavelength relative to the instruments. And then we cover in the range of observables. So this includes water vapor. These sites, particularly McDonald, can have nights with quite high water vapor where you might not get a lot out of your telluric correction, but still important to apply. You want to cover your full range of zenith angle, right? The air mass that you're observing through will affect how much absorption there is in the atmosphere. This can certainly be seen in oxygen. So up here, I show two models of oxygen, molecular oxygen transmission at two different zenith angles, low and high zenith angle. And you can see that at high zenith angle, you're observing through more atmosphere, you have much more oxygen absorption. And then you also want to cover other relevant molecular abundances. For NEID, this is not a problem. Water and oxygen are essentially the only absorbers, but in the near infrared for HPF, you start to get other things. So here are two carbon dioxide models at two abundances that have been covered over HPF's lifespan, and you can see minor differences as the carbon dioxide concentration has gone up. And so then once we have this grid, we can interpolate across it, across these, zenith angle, water vapor, molecular abundance, and then interpolate across wavelength to get models that directly reflect our observations. So great. So we now have these models that can be convolved to produce observation-like spectra. So the next step is to fit for the kind of most important free parameter in these models, which is the water vapor content of your exposure. And so to do this, what we've done is, so we're fitting water vapor across multiple small spectral ranges in each of the spectra, NEID and HPF separately. So we deblaze the spectrum, which flattens it mostly, and then we remove any leftover continuum in the region. So in here, black is some NEID data that has been deblazed and normalized. It doesn't have to be perfect, but kind of as long as it's roughly flat, you'll remove any potential continuum effects. And then you just perform a normal least squares fit of your model across water vapor to your data. There are also, I've looked into for HPF in particular, instead of casting it as a least squares, casting it as more like a least residuals based on the ratio of the model and your data to even further reduce effects of continuum mismatch, particularly for M dwarfs. So kind of importantly is that we're not just fitting a single region for water vapor, we really need to fit multiple spectral ranges. Fitting the entire spectrum is not feasible. There's just, especially for HPF, but especially for NEID, we cover just so much wavelength ground. Fitting the entire spectrum would be infeasible. Water lines are saturated. You would certainly have continuum issues. But we want to fit multiple regions because due to the temporal effects that I was talking about earlier, with stellar lines sweeping in and out of telluric bands, you will sometimes have contamination where a stellar line could bias your water vapor fitting. And so this is just a plot for one of NEID's standard star observations, the water vapor value fit in each of the spectral regions that we are currently using for fitting. And you can see that, okay, everything agrees at around 18 millimeters of water, except for this very last spectral region, which is fitting at 30, which is a lot of water and would produce an extremely inaccurate correction. But that's because in that spectral region, there happens to be a stellar line that overlaps a strong water line and is completely dominating the fit in that region. So by moving away from fitting single regions at a time and fitting them all together, you reduce the effects of stellar line contamination. And we see that we are producing much more accurate models. For NEID in particular, the previous data reduction pipeline version was just fitting on a single region. And then when we implemented this new method in version 1.3, for anyone who uses NEID to keep an eye out, we saw a dramatic reduction in the number of spectra with extremely high water vapor values that were definitely spurious and were because of stellar contamination. So great, so we now have our water vapor content. Like I said, the most important free parameter in defining these models. And so we should have everything. We can now generate a full model. We have the air mass of the observation, which sets for example, the oxygen absorption strength, or also, I'm mostly just talking about line absorption here. There's also continuum absorption, the Rayleigh scattering slope. Those are set by air mass. We set our water vapor, and then we can also include other molecules, oxygen for both NEWID and HPF, carbon dioxide, and methane for HPF. I may have said that backwards, but now this is still not quite fully done, because these molecules can also vary in their abundance that we would want to look into. Just to focus on carbon dioxide, right, due to climate change, or well, excuse me, causing climate change, right, we have levels of carbon dioxide in the atmosphere rising. These are observations from Mauna Loa and Mauna Kea of the atmospheric carbon dioxide concentration over the kind of from about when HPF started observing onwards. And you can see a steady increase over time. And so an observation in 2018 and an observation in 2024, there's relatively small differences, but you would see difference in the carbon dioxide absorption. And so we need to account for that. The way we do this is we basically just read a value off of this plot. I have looked at fitting for the carbon dioxide concentration in HPF data. That is what's shown here in black, are fits of carbon dioxide abundance or concentration in the atmosphere from A-star observations with HPF. You can see they're quite noisy. The CO2 band, while clearly present and visible, is not particularly strong, and it's overlapped by some water absorption, so fitting for it is quite difficult. But you can still see, so in pink, I've binned the CO2 concentration measurements from HPF by 45 days. And so there's an offset relative to the measurements from Mauna Loa, but the trend is consistent. And so some work needs to be done to see if that offset is true. I mean, the abundance might just be different in West Texas than in Hawaii. So that could be true, but there could also be other effects like maybe continuum issues or other contamination of the fitting. But so with that, we now have our full models. We have water vapor fixed, we have oxygen fixed with the air mass, we have CO2 fixed for HPF from these measurements of atmospheric concentration. So we now can apply our model and see how it does. So first, just to kind of take a look at the effects of the line spread function, I like to zoom in on some of the weaker lines in molecular oxygen bands, since because the strength of the absorption is fixed by your air mass, any effects on the correction are just from the line spread function, not from any sort of fitting like would be true with water vapor, where maybe your water vapor fit is not quite right. So this is a portion of the molecular oxygen gamma band in NEWID. In black is the data. You can see these kind of doublets of lines of oxygen. In brown is the best fit telluric model. And then up top, I have the correction residuals. In teal is the correction that was done prior to version 1.3 of the NEWID pipeline, which actually used a line profile that was measured from the LFC, but it was only at a single point in the spectrum. And so while it would have worked at that single point, it would not work elsewhere, as you can see here from these dramatic residuals in the oxygen absorption correction. In red is applying this top hat convolved Gaussian, LSF. And you can see that, so even that model, which we know is not perfect, is not accounting for all of the asymmetries that are present in the NEWID profile. You can see these corrections are quite good. There's still some structured residual that you can see. Some of that could be from the line profile still not quite being right. Some of that could be from the oxygen models themselves. I think if you're ever going to have some higher order effects where maybe the molecular transition line shape is not quite right, you might see that here in oxygen. But overall, this is extremely encouraging. The line profile is doing exactly what we want it to be doing in terms of improving our telluric correction. We can also take a look in HPF and compare to results from some other code. So this is courtesy of Chad Bender running the TerraSpec code on an HPF A-star observation. So TerraSpec simultaneously fits for continuum, telluric absorption, and a line spread function in the region of spectrum that it's fitting. So that line spread function model it uses is a set of Gaussians that are offset from each other at different heights, so you can account for asymmetries. So that's quite flexible and can account for line spread function variation, or excuse me, non-Gaussian line spread functions, but it can't account for variations. It's only a single line spread function for your spectrum, and let's say you're fitting a full order, only one line spread function for your full order. So for the left is a portion of the spectrum. This is an oxygen band in the HPF bandpass at about 1.3 micron. In orange here is the correction from TerraSpec, and in teal is from the models that I've created. And you can see that actually here, this is the portion of the spectrum where TerraSpec is fitting. You can see that the TerraSpec correction is quite good and actually seems to outperform, at least in this region, the corrections that I've applied. If we go further away to a different part of the spectral order, you can see that now TerraSpec is not doing as well. There are still structured residuals in both corrections, but the models that I've generated are doing better. And so I think this is a result of TerraSpec's very flexible line spread function in this region is kind of overfitting to account for issues with the model. But then when you get further away, it can't do that, and so the correction will be worse. And so this kind of really highlights, particularly for fitting, the volume of data that we're getting, having a fixed line spread function model really is super important because it removes these free parameters. You might have issues with your model still, but it removes these free parameters that will kind of inhibit the efficiency of your telluric fitting. So what about more broad correction quality, particularly of water lines, which are the most abundant across both of these instruments band passes? So here what I have shown is for a collection of A stars observed with HPF. I've selected a region where there is a small kind of forest of water lines that are of moderate strength, no saturation, but not too weak, surrounded by some telluric-free regions. And so what I've done here is compared the RMS within that portion of the spectrum, where the water line is after correction, to the RMS in the surrounding kind of reference telluric-free regions. And so you can see that out to about a precipitable water vapor column of 10, the corrections that are being applied are at the percent or sub-percent level. So that's extremely encouraging. And even beyond that, where you're starting to get very strong water absorption, the corrections are still not quite bad. They're going to be worse directly in the line cores where the water absorption is strongest, but the correction is still quite good. So this is extremely encouraging for applying this telluric correction to actual science results. Now, there are still some issues. If we take a look at a portion, this is just kind of a random portion of an HPF spectrum. I think this is within one of the Paschen lines. You can see that the telluric correction is wonderful, except, what's going on here? There's clearly overcorrection happening at this pretty relatively strong water line. There's maybe also a bit of a poor correction here, but because nearby lines are corrected fine, and I zoom in here, there are other lines that correct better of similar strength to this line nearby. So it's not an issue with the water vapor value. There's clearly something wrong with the model at that particular line. And so this is where I've come to learn quite a bit from the molecular physicists, which I was lucky enough to attend the HyTran conference earlier this year. So HyTran is kind of the state-of-the-art molecular line list database. And so I learned quite a bit. There's some warnings that I learned about generating these transmission models and using HyTran or other line list databases for producing those models. First, to be very aware of the line list being used, I got up, I gave my talk there. I quite confidently said that I was using the HiTran 2020 line list. And one of the first questions I got was, are you sure you're actually using the HiTran 2020 line list? Can you even do that with LBL-RTM? And I was kind of taken aback. Well, it turns out you can, and I was, but it was still not quite right, actually. So HiTran is kind of the state-of-the-art line list database. But the corrections are done with LBL-RTM, which is a code generated by AER. AER themselves do work on water line lists, correcting them. And you can actually see there's a difference. So in teal here is a Telluric correction using the HiTran water line list, which to me, I always assumed was state-of-the-art. And in red is with the AER line list. And you can see here, for example, see this wavelength. This is at the helium line. The HiTran list is wrong. It's overcorrecting, but the AER line list is flat. And so we have to be really careful about the line lists that we're using to generate these models and make sure that they are completely up to date. Some other warnings are just that, much of the work on these transitions is done at redder wavelengths. Higher order effects are not necessarily known, but that there are some encouraging things as well. I mean, these line lists are always improving. And they are generally reliable. There are issues from line to line, but they are generally reliable. Talking to some of the atmospheric physicists, they were pretty confident that issues with the atmospheric profile not being quite right probably wouldn't cause any major issues, which was good to hear. They didn't think that some higher order effects on transitions or line shapes would affect kind of our level of observations. And that the code to generate these models, LBL-RTM, the basis of MolecFit and TerraSpec and TelFit, is continuing to get upgrades, which is great to see. I'm running a little behind. So there are, still things to do to improve the Telluric correction. As I showed from that one line that was poorly corrected in HPF before, there are plenty of those lines across the spectrum, particularly in as we get to the visible, where the molecular physicists care less. And so I think that there's kind of ripe collaboration with AER and HiTran to fit for fixes in these line lists that could even produce greater correction quality for the tellurics. And then I think there are other things to look into regarding the atmospheric profiles, higher order effects of molecular lines. And I think the water vapor fitting routine that I described can probably be a bit smarter, particularly for dealing with stellar line contamination across spectral type. So just to kind of give a quick tour of some of the applications, the kind of science applications of the telluric correction. If we think back to what I showed at the beginning of the talk, of the temporal noise contamination of NEID's H alpha time series. Well, if we apply our telluric correction, it completely removes that noise, which is great. It's exactly what we would expect. So in red here is the time series of the activity indicators with correction. You can see it's much flatter, much less noise, no great structure. And in the periodograms, there's still a bit of power at a year in its aliases, but that power is greatly reduced. And so kind of a note for NEID users, telluric corrected activity indicators will be in the upcoming data pipeline release. So we can also apply this to RV measurements. Particular, I think that there's a lot of leverage here for something like Serval, template matching, where you generate an empirical template from all of your observations and then measure an RV from frame to frame relative to that template. Serval already does quite strict telluric masking, but now we can correct for tellurics as well and know that those corrections are quite accurate. And so here is just a comparison of the Serval template. In black is without telluric correction, in red is with telluric correction, but still using the same strict masking of tellurics to generate the template. And they're almost exactly the same, except you can see there are some regions where the template without a telluric correction might have some deviation. That could be due to telluric contamination getting through, or perhaps overfitting across masked regions. And so even without adding in any more spectral region, from the telluric correction by making that masking more lenient, you are creating a more accurate template, which will improve your radial velocities. I've only just started looking into this, but here is actually using Serval to measure RVs from HPF. These are observations of 80 Leo, which admittedly is quite a bright nearby M dwarf, so the observations are quite good. But what I show here are comparisons running Serval with strict telluric masking, with a correction on the y-axis and without a correction on the x-axis. The RVs are quite consistent, but you can see even without adding in any more spectrum, but just incorporating the telluric correction, the error in your RV is decreasing. Not by a lot, but it's decreasing. And if we make that telluric masking more lax, so we're adding in a bunch more spectrum over the same spectral orders for HPF, the RV values start to get a little bit more scattered, not necessarily surprising, not necessarily a bad thing, but you have a dramatic decrease in the RV uncertainty, which makes sense. You're adding in more spectrum just from spectral line content, information content, you would expect this. And so this is on a very bright star. I think kind of more so you would get gains on fainter objects, M dwarfs, where so much of the information content and flux is in the red, where the telluric absorption is worst. But I think this is very, very promising preliminary results for incorporating these telluric corrections into measuring RVs for HPF and for NEID. So just to kind of wrap up, there are still lingering issues that need to be addressed. The water lines and the line lists are not completely accurate across the visible to near infrared, causing some poor corrections, like I showed here. The NEID line spread function is pretty good, but needs to be upgraded to match HPF's flexible asymmetric model. And I think that the water vapor fitting of the telluric model can be just a little bit smarter, although it's doing a pretty good job, particularly with the inaccuracies in the water line list being the driver of issues. But overall, I would say these results are quite encouraging and will be expanded. These telluric corrections are often a very high signal. I showed earlier that typical correction residuals were sub%. Here is just an example correction residual spectrum for an order in HPF. You can see that there are a couple lines where there's clear line list mismatches, but otherwise, corrections are good to 1% or below, particularly for the weaker lines. I think that there's a lot of avenues for collaboration with the molecular physicists, atmospheric scientists, that would be not just for improving the line list for telluric correction, but I think would be really important kind of points of contact for, say, atmospheric studies or other information or other studies that require information about molecules that, well, at least I certainly do not know a lot about. And I think that I really hope, it's been a while since the last kind of telluric summit that I'm aware of, but, I really hope to kind of maybe cross-apply methods from other instruments and really compare qualities of different techniques and the application to science. Yeah, so I think with that, I'll just leave up kind of a bit of a summary and happy to take any questions.
Cool. Thank you so much, Danny, for an excellent presentation. Folks, please feel free to use the little clapping hands emojis if you also got a kick out of that. So what I'm hearing is that when we're thinking about RCN events for the next year or so, Telluric Summit should maybe be on the list of things we try to put together.
I think I would be on board. I would be on board.
Noted. I will hold you to that. Open the floor for questions for Danny. Please feel free to use the raise hands feature on Zoom. Okay. I see Marshall and then Andrew. So go ahead.
Hi, Danny. Really nice talk. Couple of quick questions. First, I don't think you addressed time variability of the line spread function. Have you seen any time variability, and do you always just use the line spread function from the simultaneous reference fiber observations, or can you stack the data over some time span to get a higher signal to noise reference?
Yeah, it's a great question. I've only kind of preliminarily looked at temporal evolution. I've not seen anything significant, but I would not be surprised if there is evolution, or in particular that maybe there's maybe more kind of discrete jumps at different points, say with a vacuum cycle or something like that. For measuring the line spread function, yeah. So it is not using the simultaneous observations. So what I'm doing is at a particular time, yeah, like you say, stacking a bunch of observations and measuring the line spread function. And so that way you can actually measure the line spread function in each of the fibers, because you do see slight differences in the line spread function per fiber. Again, not significant, but when we're clawing at every little bit of a percent, it matters. So at least for now, that's enough. But there is definitely an avenue for needing to be a bit smarter about that if there is significant evolution.
Okay. And then second question, this is probably a bit of not naive question, as I'm pretty new to this, but would a Fabry Perot etalon also be usable for this, or are the peaks of that too broad to really show the line spread function well enough?
Yeah, I mean, I think it depends on the etalon, but I think it likely that they could be too broad. Yeah, I mean, there's maybe something you could do with, if you have a comb, you can maybe use the comb to get a guess. And then, I mean, this is something that I've thought about for NEID, which is no longer a problem since we have blue light in the comb. But, could we use could we kind of bootstrap off of the comb to use the etalon, which maybe could be done, but I think otherwise it could be too broad. Yeah.
Okay, thanks.
Okay, we'll go Andrew and then Dinko and then Bryson. For other folks who have questions, if you don't have the raise hand feature for some reason, feel free to mention it in the chat and we'll add you to the list. Danny, I'm assuming we can borrow you for a few minutes after the top of the hour.
Yes, absolutely.
Awesome. Okay, Andrew, go ahead.
Okay, awesome talk, Danny. And I'm really impressed at the quality of the fits that you get with what is effectively almost an analytic model, which means, of course, you could shift it if necessary using the first derivative. So I wanted to ask a little bit more about the atmospheric profiles that you use. What goes into them? Do they include wind and wind shear?
No, so this is definitely an avenue that could be investigated. It's just using the kind of standard atmospheric profile. I know other codes, will pull a profile, from the time of observation or something to try and as accurately reproduce it as possible. So no, I'm not incorporating that, but I think you're right that it certainly will be introducing kind of perturbations on the model that need to be looked at. But I mean, I don't know, maybe if you have a sense, but I don't have a sense of what the kind of amplitude of those effects would be. But I think, because we're doing so well with the model so far, kind of to first order, I think we probably can start to probe those effects.
Yeah, I mean, you'd probably only see it if you were working at relatively low elevation when the wind, because the wind tends not to blow vertically. But yes, if you're facing into or away from the wind, you might see a few meters per second of shift in the lines. But I was wondering if that could be corrected for different species, depending on where they form in the shear pattern, just by adding or subtracting a bit of first derivative.
Yeah, I mean, I think it totally could. I think that's a really good idea. I have not thought about that.
Okay, thanks.
Thank you.
Hey, Nico, you're up.
Hi, I'll join the others in complimenting you on a nice talk. And I have a question. I myself have worked on reconstructing the line spread function from frequency comb data on HARPs. I'm wondering, how do you fit your lines? Do you fit them individually or across the entire shell order? And how many parameters do you use? If you could explain a bit.
Yeah, sure. So for NEID, which is definitely a less sophisticated model, I guess I should say, the lines are being fit individually, and then kind of the parameters of the profile, the two width parameters, are then fit across in order to ensure some degree of smoothness. from, say, I don't know, mode to mode issues with background subtraction or something like that. For HPF,
Sorry, just on the parameters. So you have one parameter for the width of the Gaussian, another one for the width of the dot pad. I presume you have some kind of amplitude position parameters for the line centers.
So yes, yes.
So four, for example, 4 per line.
For those, yes, it would be 4 per line, yes.
And then parameters for the polynomials.
Correct.
All right. Sorry for interrupting.
No, that's fine. Yeah, and then for HPF, this is fitting that my collaborator Joe Ninen did. But from that, what he did was kind of create a super resolution profile by in steps chunking together laser comb lines across the HPF spectrum. And with HPF, we're sampling than NEID, so kind of catching all of potential issues with the line shape will be more of a problem. And so then he goes kind of by that to fit, and I believe there he fits all of the lines simultaneously, and that's a lot more free parameters, because you have a width parameter, the line parameters, the amplitude, and the line centers, and then you also have parameters for the orthogonal polynomial that's accounting for asymmetry. So that's a much more complicated model. But yeah, that's done with kind of stacking lines across the spectrum.
Okay, thank you. And just as a comment, so when you've seen that you have effects at the edges of your orders, I have seen this in HARPS as well. My conclusion from that is, if you want to do like 1 meter per second precision, is that you should not be stacking your, you should not be merging your shell orders. Some of the things that you see later, and you showed in the Tellurics, might actually be to that if you have been merging shell orders.
I haven't been, but yeah, that's a good.
Oh, okay.
But that's a good point about, yeah, edges of orders are often smart to stay clear of.
Thank you.
Yeah, thanks.
Okay, and Bryson, go right ahead.
Yeah, actually, Andrew asked my question more or less, but I think I can still have another angle. So I'm just curious if you have observed like any, and I'm guessing the answer is no, because you would know by now, any like discrepancies just in like the fundamental, like just like the frequencies or the wavelengths themselves between the Telluric model and like the wavelength calibrated spectrum that could be explained by like a wind shear or something, but I'm guessing you would have already observed that by now.
Yeah. I mean, so do you just mean like, let's say a Telluric correction residual that's clearly kind of due to some discrepancy in the center line center?
Yeah, just like a clear like offset, like left right. But that would be like probably be everywhere across the entire bandpass. So I'm guessing the answer is no. But
yeah. There's nothing, and granted, NEID we have a lot of data, but it's all kind of stellar observations with a lot of lines. HPF, we have tons of A-star spectra. I have not sifted through all of them. It's very possible that one of them has this, and I've not seen it. But yeah, nothing kind of consistent across the full order. You will see plenty of poorly corrected lines from the line list due to line center issues, but that's from the line centers themselves in the Telluric models. Something I didn't quite appreciate talking at the High Trend conference with people was that, in my mind, I was always imagining the line strengths being the problem in the line lists, which they are, but it's really apparently the line shifts and getting the line centers right that is the predominant problem. So there definitely are clear residuals from mismatched line locations, but it's from the line list, not from, at least as I've seen so far, not from, conditions or anything.
Gotcha. Yeah, thank you.
Okay, thank you, Danny, for indulging the questions after the top of the hour. Why don't we call it there so folks can move on to their next meeting of the day. But thank you all again for calling in. Thank you, Danny, for a wonderful presentation. And again, we'll be back in October with Christina Hedges talking about software development in astronomy. So I'll catch you all then.
Thank you, Jen.
Yeah, thanks, folks.